we'll now look at our other force equation. So we'll be looking at Q2 equals R3 in this one. And so here we have F1 dot dr1 plus F3 dr3 minus dv dr3 dot dr3 equals 0. Now this is an independent equation, okay, and so we need to get everything in terms of R3, and so we'll do similar to what we did in the last video. We'll do dr1 dr3 dr3 plus F3 dr3 minus, and then we'll plug in our expression for dv dr3, which was k r2 minus r2 naught sine theta 2 dr3 equals 0. Now this term goes to 0 because those two are independent variables, and we're left with F3 dr3 minus k r2 minus r2 naught sine theta 2 dr3 equals 0. And so that gives us F3 minus k r2 minus r2 naught sine theta 2, all that multiplied by dr3 equals 0. If we assume that dr3 is not 0, then we can divide through by it, and we'll get an expression that allows us to say F3 is equal to k r2 minus r2 naught sine theta 2. Okay, and so that'll be an expression for our forces on this. Now, this is all kind of interesting. And so suppose, on the other hand, that we wanted to just see how this is going to work out, suppose that we want to, for a moment, say that k r2 minus r2 naught is equal to some tension in the bar, in the spring. Then we'll have our two expressions look like F3 equals t sine theta 2, F1 equals minus t cosine theta 2, and we could solve those in terms of t, and we would have t equals F3 divided by sine theta 2, and so we could say F1 is equal to minus F3 cotangent of theta 2. And so even though the motion of those sliders is independent of each other, okay, the forces that we will have to put on those sliders to hold them at equilibrium are not independent of each other. And so they're just going to be related by the cotangent of theta 2. All right.